Hello, everyone. This is Rajdeep Biswas. I'm a director of advanced analytics and machine learning here at Microsoft. Uh, Standard disclaimer, this talk is academic in nature and expresses my opinion and personal experience on the subject. Companies are investing a great deal of time and money to develop analytics that deliver faster, better business decisions. But deployment, the infamous last mile of analytics, is still a challenge, with many development projects never being deployed at all. Nearly every organization today is on a journey of digital transformation, which requires being able to exploit data and tirelessly apply real time insights to drive business decisions. The pace of spending continues to accelerate. In 2019 alone, IDC estimated that organizations invested 190 billion in analytics. By 2022, they predict the spending will increase to 275 billion. However, despite such massive investment, less than 50% of the models gets deployed. 90% of the models takes more than 3 months to get deployed. 44% of the models take over 7 months to put into production. The lost effort and return on investment represented by vast number of undeployed or delayed analytical efforts is staggering and increasingly unacceptable to the business leaders. Now, before we go into MLOps, a little bit about Center of Excellence. A Center of Excellence is a body in an organization that works across business units or product lines within a business unit and has a leading edge knowledge and competency in that area. It is comprised of highly skilled individuals and experts who disseminate knowledge in an organization and shares best practices. MLOps empowers data scientists and app developers to help bring ML models to production. MLOps enables us to track, version, audit, certify, reuse every asset in your ML lifecycle and provides orchestration services to streamline managing this lifecycle. Companies are investing a great deal of time and money to develop analytics that drive faster, better business decisions. But as I said, the deployment, the infamous last mile, is still a challenge. Now, MLOps is all about how you are going to bring the ML into production. MLOps, or sometimes which is also called DevOps for machine learning, is bringing the best practices of software development to data science. MLOps helps data scientists and app developers to bring the ML model into production, right? But there are a lot of challenges in doing MLOps. We might have built a machine learning model that exceeds all accuracy expectations and impress our business sponsors. Now it is time to deploy the model into production, and it might not be as easy as we had expected. There are likely many things to put in place before our model can be used. Over time, someone else might develop a new model that can do better than the old model. The question we must ask is, can we implement it without disrupting our business? It might be necessary for regulatory purposes to recreate the model and explain the model's predictions if unusual or biased predictions are made. Data inputted to our training and model can change over time. Because of these changes, it might be necessary to retrain the models periodically to maintain the accuracy of its predictions. Who is responsible to feed the data, monitor the performance, retrain the model, and fix if it fails? If we experience all these challenges and more, we might want to consider implementing a machine learning DevOps strategy for our project. At a high level, MLOps refers to the application of DevOps principle to AI-infused applications. And here, we are trying to explore the most common high-level challenges in MLOps and machine learning pipelines. And as we can see, they are a mix of communicational and technical challenges. Some more challenges out here. And all of this are going to get addressed by MLOps and the core principles that it follows. Moving on. So how does MLOps looks like, right? We have to train the model that solves a real business problem. And then the model needs to be packaged in a format which can be used somewhere else, because where the model gets developed, not necessarily the model gets used there. And then we need to validate the model behavior in terms of its responsiveness, regulatory compliance. And then we need to deploy the model that can be on heavy edge, light edge, or on VMs. And then last but not the least, we have to monitor the model for its behavior and business value. We need to know when to replace or depreciate our stale model, and then connecting it all together and forming the circle is the retrain loop. Depending on the model monitoring results, we need to retrain the model and repeat and rinse. We are also going to look at here some of the components of MLOps lifecycle. Both DevOps and MLOps aims to replace a piece of software in a repeatable and fault-tolerant workflow. But in MLOps, that software also has a machine learning component. We can think of MLOps as a specialized subset of DevOps for machine learning applications and projects. However, there are some major differences also between classical DevOps and MLOps. Because in MLOps, for example, the exploration precedes development and operations. Data science lifecycle requires a new adaptive way of working. It definitely requires greater operational effort, and machine learning teams require specialists and domain experts. Where I'm trying to arrive is MLOps lifecycle is extremely complex process, and it needs a lot of different personas to make it work in a proper fashion. The benefits are, of course, automation and observability. You can audit everything is code as a service. Everything is repeatable. We can validate and compare model quality, minimize bias, and provide descriptiveness. The reproducibility and auditability I already mentioned. So in a nutshell, MLOps offers velocity and security for machine learning. Now, very importantly, whenever we are talking about MLOps Center of Excellence, we need to talk about MLOps maturity stages, because all organizations and teams are different in their own way. The MLOps maturity model helps clarify the development operations, principles, and practices necessary to run a successful MLOps environment. It is intended to identify gaps in an existing organization's attempt to implement such an environment. It is also a way to show you how to grow your MLOps capability in increments rather than overwhelm you with the requirements of a fully mature environment. As with most maturity models, the MLOps maturity model qualitatively assesses people, culture, processes, structures, and objects or technologies. As the maturity model increases, the probability increases that incidents or errors will lead to improvements in the quality of the development and production processes. There are, and this is not an exact science, so there are different definitions of MLOps maturity stages. Uh, this is the one which I found to be most applicable in practical scenarios, from level 1 with no MLOps level and to level 4, where the training and release are operationalized together. I'm not going to read it line by line, because in the coming slides we are going to double click, because this is the core of the talk. This defines the MLOps Center of Excellence. Most of the organizations start at level 1 with literally no MLOps. So in the model creation phase, data is gathered manually, compute is likely not managed, experiments are not tracked, results may be in a single model file, manually handed off with inputs and outputs. Now the model release also is a manual process. A scoring script may be manually created after experiments, not version controlled. Release managed by data scientists or data engineers alone. And in terms of the application integration, it's heavily reliant on data scientists' expertise to implement. Manual releases are done each time. So that's where most of the organizations start. Moving on, level 2, where the model training is reproducible. So in terms of the model creation, data pipelines gathers data automatically. So that's one step forward. The compute is managed, which can be hybrid in cloud or on-premise. The experiment results are tracked. Both training code and resulting models are version controlled. The model release, it's still manual, but the scoring script is version controlled with tests. And the release is managed by software engineering teams. In terms of the application integration, basic integration tests will exist for the model. However, it is heavily reliant on data scientists' expertise to implement the model. In level 3, we are in the realm of automated model deployment. So in the model creation phase, the data pipelines, as we saw in level 2, gathers data automatically. The compute is managed, the experiment is tracked. Both the training code and resulting models are version controlled. The model release is automatic in nature. The scoring script is version controlled with tests, and the release is managed by continuous delivery aka CI/CD pipeline. The application integration is less reliant on data scientist experience to implement a model, and the application code has unit and integration tests. In a nutshell, in level 3, you can package, you can certify, and deploy a model in an automated way. Which brings us to level 4, which is a fully mature MLOps uh, capability that an organization can have. Here, in the model creation phase, the data pipelines gathers data automatically. The retraining is triggered automatically based on production metrics. Very important, right? Compute is managed, experiment results are tracked, and both training and resulting models are version controlled. The model release goes without saying is automatic. The scoring script is version controlled, and the release is managed by continuous CI/CD pipelines. The application integration is less reliant on data scientist expertise to implement a model, because unit and integration tests accompany each model release. Now, this is complex, undoubtedly. I'm not going to go line by line in this architecture because we have another architecture slide shortly. But this brings me to a very important discussion in terms of MLOps personas and roles, right? And data scientists and engineers have a mismatch of approach and skills in their work. Making it easy for the data scientist and engineer to work collaboratively becomes a major consideration in the MLOps process flow. It does require new skill acquisition by all team members. There is a need to unify all of the principal personas without alienating anyone. A way to do this is to make sure they share a common understanding of conceptual models for MLOps, agree on clear expectations of how all the team members will work together, discuss working guidelines to achieve common goals. The business stakeholders and data end users may require a way to interact with the data output from the models. A user-friendly UI is the most common solution. Now, with that being said, let's take a look at the generalized MLOps process. And in the next slide, we are going to double click this. So the data scientist starts the first part of the process, potentially working with the data engineers to access and understand the data, EDA, feature engineering, etc. The data scientist then creates the model and registers the model in the model registry. The ML engineer then creates the pipelines and processes for releasing the models and deploying. The models can be deployed via multiple ways if it is containerized. Once models are running in production, they should be monitored, and when required, maybe a data drift or underperformance from the models, model retraining should be triggered and the life cycle continues. Double clicking this architecture, reveals the end-to-end MLOps process. And while there are multiple layers in this architecture, they all follow some core MLOps principle. Number one is the continuous integration. So testing ML system comes down to testing feature engineering scripts, validating data schema, evaluating the model, and validating the ML infrastructure, access permission, model registries, inference services, etc. And then comes continuous delivery in the context of ML, that is the capability to automatically deliver artifacts to different environments like dev, stage, production. And really, a ML artifact consists of feature engineering pipeline, a model, and an automatic retraining pipeline depending on the use case. Then comes continuous monitoring. It is mandatory to provide a consistent feedback loop, as you can see in the architecture, from model prediction results in production. The only real model test is in production where the model is fed live data. Hence, not having a monitoring system in place to enable ML practitioners to renew model predictions may have catastrophic consequences. Last but not the least, the continuous training. And here we are trying to attain a high level of ML autonomy. The ML systems should be able to automatically detect data drifts or be triggered based on business rule to retrain models in production. The principle, however, can only be applied if a monitoring system is running to ensure that the retraining is activated in predefined conditions. Now, the above architecture can be implemented by using both GitHub Actions and Azure pipelines in conjunction with Azure Machine Learning. GitHub Actions and Azure pipelines, as you know, have a common history. In fact, the Actions agent is a fork of the pipelines agent. Pipelines are very important because pipeline as code, it benefits from standard source control practices. It can be audited for changes just like any other files in the repository. Doesn't require accessing a separate system or UI to edit. Can fully codify the build, test, and deploy process for the code. And can usually be templatized to empower teams to create standard processes across multiple repositories. We can use the Azure DevOps project for build and release deployment pipelines, as well as GitHub Actions, along with Azure Machine Learning Services for model retraining, pipeline, model management, and operationalization. The build pipelines include DevOps tasks for data sanity test, unit test, model training on different compute targets, model version management, model evaluation, model selection, model deployment as real-time web service, stage deployment to QA prod, and integration testing. Let us quickly look at the branching strategy. And again, this is not written on stone, but just a sample. So we can create a dev branch from the main, where one can create sub branches for feature engineering, hot fixes, and whatnot. And the continuous integration consists in running linting, unit tests, data checks, etc. And finally, publishing an ML pipeline, either training or serving. Any changes applied to the main branch must be done through a pull request. The approved pull request may trigger a continuous integration process in test or prod. And I think this is the standard branching strategy that's followed in the industry. And then lastly, I always want to finish any machine learning talking about responsible AI, which is really all about how we design, develop, and deploy these AI systems that are fair, reliable, safe, and trustworthy. And to do this, we need to think of responsible AI as a set of socio-technical problems. We need to go beyond just improving the data and the models. We also have to think about the people who are ultimately going to be interacting with these systems. Throughout the deployment and use of AI systems, trust must be at the core, trust in the platform, process, and models. Thank you. I really appreciate your time.